it either way, and we'll see. All right. So let's start with the first example from this. First example, graph the relation 1 comma 1, 2 comma 1, 2 comma half, 3 1/3, and then 4 1/4. That's what we're going to do. We're going to graph this relation. Now, it's defined as a relation in the beginning because we don't know whether or not it's a function just yet. You might be able to tell right away, but what we're going to also do for this problem is determine whether or not it actually is a function. So if I were to graph something like this, okay, I know what's my biggest y value in this ordered set of data? What is my biggest y value? And the smallest? Good. So I'm only going up to 1. So on the y-axis, we can just go up to 1 here. Maybe draw another tick mark at 0.5. Okay. Along the x-axis, though, we're going from 1 all the way to 4. Again, the x-axis, or the independent variable, right here goes from 1 all the way to 4. So here, let's draw 4 tick marks. And keep that in mind, and I know I haven't really gone over a lot of, labeling axes and graphing techniques, but when you graph, you want to choose your values along the axis according to your data. So our data here only goes up to 1 on the y-axis, so that's all we've done here. And notice our y and x-axis have different increments. It goes by 1 along the x, but 0.5s along the y, which is fine. You can always do that. So quickly graphing the 4 values. 1, 1 is our first data point. 2, 1 is our next data point. 2, 1 half. Then 3, 1/3. And then 4, 1/4. So there's our 5 data points in green. Pretty easy, right? Just to graph those. We've done that many times. Now somebody tell me, is this a function? Why?
Because you put 2 into the function and you get 2 different outputs.
Very good, Summer. That's exactly right. So again, when you place the number 2 in for the independent variable, you'll see that you get 2 different outputs. One of those is 1, and the other one is 1/2. So if an input has multiple outputs, by definition, it is not a function. So again, here's what you can remember. If you see the independent variable or the x coordinate repeat itself with a different y coordinate, it's not a function. It's not a function. Now, how can I see that graphically? How can I see that graphically? That's right, very good. What kind of a line is this? There it is, vertical. Good, that's exactly right. So take a look, when I put a vertical line through x equals 2, I'm going to see that it intersects twice. It intersects here and here. Those are the 2 locations that were from the values in blue that we've circled here. Those are showing that if you intersect the vertical line twice, it's not a function, because that's what a multiple output is. Multiple outputs means that the width of 2 has more than one height. It's got a height of 0.5, and it's got a height of 1. Again, because of the vertical line test. Now, later in the year, and I think we're going to get to it because we're doing really well this year. We're ahead of last year's pace. We're going to get to a topic called inverse functions. And inverse functions utilize the horizontal line test. And it's the same idea, but now we're looking at a horizontal line. So keep this in the back of your mind for vertical line test. Any questions on this example? Yes?
How would the horizontal line test work if, x is generally a independent variable?
So when you do the inverse by definition is switching the dependent and independent variables and then resolving for y. And that's what causes you to use the horizontal line test, because it's like you're switching the domain and range. Okay? That's why. Very good question. All right, in definition, the vertical line test tells us that a relation is a function if and only if no vertical line intersects the graph at more than one point, which is what we just said. You don't need to write it formally if you know what we were saying a minute ago, but that's the formal definition with 2 examples. What kind of a graph is this on the left? What do we call that shape? Parabola. Good, parabola. Now, any parabola, I will tell you right now, any parabola is a function. And think about the shape of a parabola. It's always either a U or an upside down U. So by default, you're only going to intersect once. You're never going to intersect twice. Now, what does this look like? A parabola that's done what? actually, just so you know, that's what that function is, whereas over here, this was that function right there. That's y equals x squared. This is y equals plus or minus the square root of x. Well, take a look. You see more than one intersection in this example, oops, here and here. So automatically it is not a function. Okay, not a function. All right. Relatively easy enough. Let's look at the next one. Take a minute to write it down, please. Given y equals 2x squared minus 3x plus 5 with a given domain. So now we have the x values. We're given the domain or the independent variables. Find those three things. So we're looking for the range for part A, a graph of the function y, or the relation y, and then the third question, is y actually a function? Part A, what do we got here? What can I do? Something.
You can make like a chart, I guess.
Very good. Make a chart, make a table, please. Summer, what's going to go in the x column? How do you know, and what is it?
Domain.
Good.
So you're going to -3, 2, 5, and 7.
Hold on. Again, the domain, as we said yesterday again, the domain are just the independent variable values. So automatically, we know that whatever was given in the domain goes under the x column. How do I get the y values, everybody? What do I do here? Just plug it in. Just plug it in. Now, you're going to want to do this all by hand? No. So what are you doing, Nick?
Calculate.
Yeah, go to y1, please. In y1, type in the parabola or the quadratic relations 2x squared minus 3x plus 5. Type this in, and remember, have your function or your table set up as ask. Remember, go to your table settings, and under the independent variable, please select the option that says ask and not auto, so that you can ask these four values and you don't have to sit there and scroll through them the whole time. Again, how do you get to table setting? You press second table. Okay, so press second table, make sure your independent variable has ask highlighted. Our independent variable again is x. Oh, sorry, second window for table settings. We'll go down to independent, we'll go over to x. So second window to bring up table settings, that's my mistake. Second, and table settings. Go down, go over, and enter on that, and go y equals, yeah, and now go to your second. Mr. Moses. Yes?
Should you call my independent variable be asked, or do you choose?
The dependent is always auto, because you want it to calculate it on its own. You don't want to ask a value of y, you want it to automatically calculate the value. Peter?
Oh, no,
If you have a problem, if there's something that's going wrong, please raise your hand, so I know. Good, Mr. Grant, go to the second table. Did you change your settings or no?
Yeah.
Okay, good. Remember, guys, if you want to clear your table values, just press the delete button. You press the delete button, it'll get rid of all the table values that are in there already.
When I enter the explorer, it doesn't let me like enter the equation process.
Okay, because you have it on the setting called math setting. I'm going to change it. Trust me on this one. It's better to have it. See here, I'm going to go to classic instead of math. I was under mode. If you want to change back mode, I'm going to scroll down to classic. And now when you go here, you can just use the square. That's much easier. It won't make it look like that.
So what do we get? Somebody give me the four values, please. Mike,
32, 10, 40,
calculus. We have to make sure that we get the calculator stuff, guys. For real, because you're going to use it on your SAT, you're going to use it on your AP calculus exam.
I don't get the calculator.
Okay. Ask me, Peter, wow. Ask me, Johnny, which part? You want me to just go over the example of it on here? Would that be better if I just did this? So I go to y equals, okay, I type in my function. I press 2x squared minus 3x plus 5. Oops. Thank you. Didn't see that? All right, now I go to second, and then I hit window to bring up my table settings. See the table setting above there? I press second, then I press that button. I go down, I want my independent variable x to be able to be chosen by me. I want to be able to pick the x values. So I change that, I go over to ask, and I hit enter. I want the calculator to automatically figure out the values of y, so I leave that on auto. Then I press second, and then I hit graph, because second graph brings up this function here, which is table. Then in my x values, I just type in. So I press the negative down here, 3, enter. Then I press 2, enter, 5, enter, 7, enter. Okay, and those 4 values are the 4 values that we got for our actual table values. Okay? Again, guys, throughout the year, if something doesn't make sense in the calculator, raise your hand and ask and we'll go over. I want to make sure we're all on the same page. Part B, graph the value or graph the relation y. Quickly, a sketch of that. I'm not going to graph it really because look at these numbers. A sketch, I go over 3 and I go up a little bit, somewhere. I go over positive 2 and I go up further than 3, or I only go up to 7. So I'm going to go over to 2 and maybe only up a little bit. Then I'm going to go over to 5 and up 40. So that's going to be above here. And then I go over to 7 and go up to 82. It's going to be all the way out here somewhere. Okay, why did I graph this? What does that enable me to do right away?
Oh, you can do the,
Yeah, the vertical line test. Does it pass or fail?
it passes.
Yeah, it passes. Because put a vertical line through any of these points. It's not going to intersect any of the other points. Vertical line, vertical line, vertical line, vertical line. It does not intersect more than once. So anytime you put a vertical line, it's only going to intersect once. So, part C, is it a function, everybody? Yes, because it passes the vertical line test. Or just look at your table. Do you see any repeating x values here? Does anything repeat? So automatically it's a function. If your x values don't repeat, it's not possible to not be a function. Okay? No, I should not use a double negative there, sorry. All right, let's take a look at the third and fourth examples. Now, these were a little bit tricky yesterday in the other sections, so make sure you keep up with what I'm saying here. Okay? And this is probably one of the first times you've seen this before. So this is probably new material to most people. It might be a repeat to some, and that's fine. But I think this is new. Now, the problem does not ask us to graph, it does not ask us to find y values or x values, though it does say, give the domain. Give the domain. Well, I know you're all ready. Give me one sec. Look at the last example. Weren't we given the domain in this example, those 4 values? So we were told a restricted domain. It wasn't any number. The domain were literally 4 numbers, -3, 2, 5, and 7. Now, we need to figure out what can the x values be? What are the possible values for the domain values in this problem? What are the possible values that enable us to do this problem? So, in the first example, letter A, give me a value for x. Any value, somebody. Nick. 2. It's funny, yesterday I picked 2 also. Same thing. If I choose 2 for x, and I plug in a 2, what do I get for y? 1/8. Again, plug in a 2 here, you're going to get 1/8 for the y value. Pick another number. Pick a negative number. Somewhere. -6. If I plug in -6, what do I get? 1/40. So no matter what it looks like I plug in this case, I'm still going to get some answer for the y value. Do we all agree with that? Now, before I write down the answer to part A, let's look at the difference now in part B. Pick a value that function not to give me a y value?
0.
0. Explain.
Because the domain is undefined.
Yes, very good, Michael. 1 over 0 is undefined, right? If you put 0 in for x, this denominator becomes 0. So that's the restriction. But in this last problem, was there any restrictions? Or were there any restrictions? What's the only thing that would make this denominator negative? If x squared were equal to what quantity? What would make the denominator negative? 0. What would make the denominator 0? If x squared equal to what? Yeah, if x squared were negative 4, it would be negative 4 plus 4 equals 0. Agreed? But if you square a number, do you ever get a negative? The square of anything is always what? So that means that I can't find a number for x to plug in that will give me a negative 4 here. It's not possible. It's imaginary. And we're going to talk about that this year also, imaginary numbers. And the reason is, if you try to take the square root of both sides, you're taking the square root of the negative number, which we said is not possible. So for this value, or this first function here, there are no values for x that cause this to be undefined. So what values can x take on? What can we say? Which are categorized as what? All. Very good. So the domain for this problem is x are all real numbers. You can write the words all real numbers, or you could just do x is in the set of real numbers. Again, the domain just means that x can take on any value. X can be any number you pick. It doesn't matter. It doesn't matter. So far, so good? All right, Michael, you started the second part, or the second problem, by saying that 0 would cause the denominator to become undefined. And I agree, or the equation, or the function is undefined. Now, I don't want the denominator to be 0, so I can say the following. What values would cause this? What values would cause this to be 0 or not to be 0? And in the last class yesterday, I wrote an equal to sign here. It really doesn't matter as long as you understand the interpretation. So I'm going to explain that in a minute. Michael, you said that 0 would cause this to be undefined, or would cause this denominator to become 0. What other value of x would cause the denominator to become 0? What other value plugged in for x? So the sides on it. Nay? Negative 2. How come, Eddie?
Because it's a 2 there.
So what would that cause this parentheses to become?
It'll be negative 2x.
No, you have to write the first time, Manny. If negative 2 is the x value that throws us off, what happens if I plug a negative 2 in right here? What does this become?
Negative 2 plus
Yeah, which is just 0. So what you want to do in this problem is think about this as if you're factoring. Do you remember factoring quadratics from last year? Some of you might have done it, some might not have yet. When you factor something, you make a t-chart below it, and you set each factor equal to 0. Show of hands and be honest, how many people have seen this before where you make a t-chart? Okay, so what I'm going to do is just quickly explain what I mean. This is the variable x multiplied by the quantity x plus 2. When you multiply two numbers, how do you get 0 as a product? What must one of those numbers be? 0. So theoretically, x could be 0, or this quantity x plus 2 could be 0. Because I'm multiplying these two things, agreed? I'm multiplying this x by this x plus 2. So either of them could be 0. So we have to go ahead and set each factor equal to 0, and then solve each of these equations. Is there anything to solve on the left here? No, it's x equals 0, you're done. But over here, how do I get rid of the positive 2? Yeah, by subtraction. So Manny gave us the answer of x equals negative 2. That would throw this off, and I agree with him. So x equals 0 and x equals negative 2 are the two values that cannot be in my domain. They cannot be in the domain. Why then? Why can't they be in the domain? They make the function undefined. So this answer for domain, I'm going to write at the top here. The domain for this problem, we can say x is in the set of all real numbers, but x cannot equal 0, and x cannot equal -2. I'm running out of room. Okay? X is the set of all our numbers, but x cannot equal 0, and x cannot equal -2. And if you prefer to write that in words, that's fine, because that notation is not always used. You can write in words, x is in the set of all real numbers except for 0 and -2. Okay? Except for 0 and -2. So if you want to write down a rule, quote unquote, when you have a denominator, see what makes it 0. When you have a denominator in a function, figure out what makes it 0. Figure out what makes it 0. And those will be your restrictions. We call these domain restrictions. And you're going to see this a lot in pre-calc when you look at piecewise functions, and in calculus when you look at integration. You can look at integral from one value to another, from -3 to 4, so you have a restricted domain. Okay? A domain or x values. Let's take a look at part C now. Alejandro, sorry, go ahead.
How would you like the first thing? Set x plus 1.
Yes, exactly. You would do the same thing in the first one. So in the first example, very good question, you would still set the denominator equal to 0, but when you do that, you move it over as a negative, don't you? So there's no solution to this. The solution is imaginary, because if you try and take the square root, you try and take the square root of -4, it's an imaginary answer. So in the set of real numbers, it could be any value. But there are limitations to our domain, but that's in the imaginary plane, which we haven't even gotten into yet. So when you do this first one, there are no values that cause this to be -4. And that's more common sense in a sense, because when you square a value like x, you can't get a negative answer. So this here for real numbers is not a true statement, that is a false statement. A square of a number cannot be negative. That's why there was no answer for x in the first problem. All right, let's go to part C. And let's think about part C with regards to what we just said for part A, where we can't take a square root of a negative number, right? Remember again, if I try to solve for x, I get x equals the square root of -4. But I can't get that value because it's imaginary. So remember, you can't take a square root of a negative number. With that in mind, let's look at part C now. How do I write some sort of a beginning to this? Or what values can under the radical take on, or can the radicand take on? What values can the radicand be? What did you say there? Well, what can you not have under a radical? A negative. So what values can be under the radical? Positive or 0. Agreed? Positive or 0. So we set the radicand greater than or equal to 0. Again, if the radicand has to be positive or 0, positive is greater than 0, and 0 is equal to 0. So greater than or equal to 0 means that this radicand will be positive or greater than 0. Easy enough. And now solve. Add x to both sides. And write this in the other form that we were used to. Switch the order of everything. Okay, we write that for just ease of use. So what does that tell me? In words. Somebody just read it. What does it mean? X is?
Less than or equal to 2.
Yeah, that's my solution for the domain. The domain, is x. X is in the set of all numbers less than or equal to 2. That's all it is. It's a restriction. So what numbers are not in the domain? Give me an example of a number that's not in the domain. Any number. 3. Give me another number. 12. Give me a decimal number. 2.00. Good. I like that. 2.001. It is not in the domain because it's got to be less than or equal to 2. Again, so what's your rule here? Somebody give me the rule for the radicals. If you just have a radical without a fraction. Then. Perfect. Perfect. So in words, you might want to say the radicand, set the radicand greater than or equal to 0. Set the radicand greater than or equal to 0. Notice I didn't also spell that first. The radicand greater than or equal to 0. We all know the definition of radicand, what it means? Okay, so let me explain this using words that aren't here. square root symbol is called a radical. R-A-D-I-C-A-L. Radical. The radicand is the expression underneath the radical. It's whatever's in the square root. Again, whatever's in the square root is what this is, radicand. So we set it greater than or equal to 0. All right. Part D is a variation of part B and C. Can somebody explain why that is? Why is part D a combination of parts B and C?
Because the radical is in the denominator.
Yes. We now have a denominator like we did in part B, but we have a radical in that denominator. So, the rule was to set the radicand greater than or equal to 0. Agreed? But what do we know about a denominator? What can we not have in the denominator? Manny? In the denominator, not the radical. 0. So I want to set it greater than or equal to 0, but we know it can't be 0 because it's in the denominator. So instead of greater than or equal to 0, just greater than 0. So let's take our radicand now, 2x minus 8, and set it greater than 0 instead of greater than or equal to. Because yes, you want to do that because it can be positive, but it can no longer be 0 because it's in the denominator. So what's the rule here? In words, give me the rule for this one. What's my rule? If I have a radical in the denominator, what am I going to do with it? That's it. The radicand is greater than 0. So instead of greater than or equal to, you're just going to write it as greater than 0 whenever it's a radical in the denominator. A radical in the denominator has to now be just greater than 0. Because it can't be equal to 0 because it's in the denominator. So by default, it's just greater than 0. Solving, what do I get?
X is greater than 4.
Good. Domain notation, how would I write that? Somewhere on this board, I don't know where. It's right over here. Okay, domain notation. Domain equals, or set notation from the last one.
The domain is equal to all real numbers greater than 4.
Good. All real numbers greater than 4. Okay, all real numbers greater than 4. Very good, Emerson. Okay. Domain is all real numbers greater than 4. Here's a fun or trivia question for you guys, and I don't know the answer to it, so I'm asking if you do. What is this kind of a parentheses called? You don't know? I don't know.
Fancy
It
parentheses.
was like,
What does that mean called?
It was, yesterday he was giving us like a lesson about weird symbols.
And it was in there?
Yeah, it was.
yeah, like the
And
ampersand.
you don't remember? The ampersand, I know. That's the and symbol.
Wait,
But the squiggly bracket, what is it actually called?
What's that called? That end symbol?
Ampersand?
Are you the kid
Yeah.
to know?
A-M-P-E-R, and then
Ampersand.
sand.
There you go.
Yeah, and I always.
That's the bonus question I always get wrong.
Ampersand. Ampersand. So nobody knows the squiggly one?
No.
Take a look it up. Let's go to the next problem. After the next problem, we'll look it up. Once we have enough time. We will have a minute and a half or two. All right.
Oh, because I was just wondering why we did past tense only.
Thank you, sir. All right. Example. He does that over and over. So, for this example here, we're defining a function, f of x equaling 2x plus 1, and g of x equaling x squared minus 3. And what we're asked to do is find the value of this function at a certain location. Okay, at a certain location. Have you seen this before, at least part A, something like that? Show my hands if you've seen it. And obviously, guys, just be honest because I want to know. Good to know, okay. So what this means, let me translate in words for you. And this is what you might want to write down. This right here means, what is the value of the function f? Again, part A means what is the value of the function f when x equals 2? This means right here, what is the value of the function f when x is equal to 2? How do I know that that's what it's asking? Well, take a look. The function was f of x. And now x has been taken the place of, or x has been replaced by the number 2. So by default, we want to know what the function is, no longer with x, but when x equals 2. In calculus, you would say, find the height of the function at the location 2. Or at the location when the x-coordinate is 2. Okay, find the height of the function. So we're trying to find the height or the y-coordinate of this function. So go ahead and plug a 2 in. What do you get? Do it again. You're not going to write it down. 5. Right? Plug a 2 in right here. 2 times 2 is 4. 4 plus 1 is 5. I'll write it to show, but you do not have to write this down. And we're plugging that into the function f. So, make an answer.
Next one, that would be -6.
So you're plugging, tell the class what you're doing now, so we know.
Plugging -3 into the equation
Of which one?
Oh, G.
Good. So we're taking -3 and plugging it in here. Well, -3 squared is 9.
So it would be -12.
Oh, you were right the first time. -3 squared is 9, and 9 minus 3 is 6. The first time was right. Thank you. Good. So this is an answer of 6. Now, before I go on to the next one, I want you to understand that you can write these as an ordered pair. You need to be able to know that you can write it as an ordered pair. What was the x-coordinate in part A? And what was the y-coordinate? So I'll write it as? Next one. Summer? Good. -3, 6, and 2 comma 5 now. So, again, you're finding the height of the function, which is really the y value. So once you know the y value, just simply write it as an ordered pair. Part C. Somebody else. Part C. Somebody has an answer one yet. Just plug it in here. Jules, what do you got? -3. Agreed. So as an ordered pair, -2, -3. Any questions on A, B, and C? So what are you doing? Somebody explain to us what we're doing with this. In your own words, what is happening with these problems? Nick?
You just plug in here.
Yeah, you just plug in the x value, that's it. This is in a sense like substitution method. You're substituting in. You are evaluating the function. Let's write that word down, please. You are evaluating the function, and I'll use a few more words. Evaluating the function at a specific location of x. You are evaluating the function at a specific location of x. So far, so good? Okay, so we're just plugging in, that's it. Parts D and E are no more difficult than parts A, B, and C. They are no more difficult. We just have to think about what we're doing now. So, you have the answer before it?
I don't have the answer.
Okay, that's what I want, exactly. I want you to explain how to do it.
No, well, since you can just plug the equation from f in the equation.
Okay, so Alejandra, you plug the -2 in for f into f function, good. You get an answer, and then what do you do with that answer? Into the outer function g. Very good. So f of -2, when you plug a -2 in for f, didn't we do that already? And we got this -3 here? Remember when we plugged f of -2 in, we got -3? So I can use substitution method and say, these things are equal to each other. So replace this underlined part with just the number -3. So really what this is asking us to do is plug -3 into g. But haven't we done that already also? Didn't we do that in part B? What did we get when we did that? So g of f of -2 is just 6. This is called a function composition. Please write that down. When you take a function and evaluate it within another function, it's called a function composition. C-O-M-P-O-S-I-T-I-O-N. Function composition. Example D was quite easy because we have those values. Somebody step me through example E. Step me through example E, please. Mike.
Plug 5 into
G of 5 equals? I missed what you said, sorry.
5 squared minus 30.
Good, which is? Perfect. So G of 5 is 22. So Mike, what are you going to do with the 22 now?
Plug that in.
Good. So we're replacing the g of 5 here with 22. So we're really doing f of 22. So this is substitution method. You substitute that right in there. And then, Mike, what do you get? 45. Very good. So again, if I were to write a rule down here for myself, I would say work from the inner part to the outer part. Work from the inner part to the outer part. That, for this kind of a problem, you can't, because you're not looking at the exact value or the exact location of x of one function. So there's no ordered pair for those ones. These are not ordered pair terms. These first ones are. Okay, very good question. Now here's a challenge problem for you, since we have a minute left. Actually, I told you we'd look up that term. You know, I want to do this challenge first. Hold on. Here's the challenge. If f of x is equal to x squared plus 3x plus 1, and I want to know the value of f of x plus 3, not 3, but x plus 3. I'm not asking for a numerical value, but now I want a variable term to get substituted in there. How would I do this? What would I do? What would I do? Katarina? Yeah, this x plus 3 replaced this x, didn't it? So wherever you see x here, put x plus 3 now. Okay? And then, what would you do to make it look nice? Good. Or simplify. X squared plus 6x plus 9 plus 3x plus 9 plus 1. Again, how did I do this part? I thought of this as FOIL. Remember, you cannot distribute the square to each term. You have to think of it as foiling. So we write that as a FOIL term to get this. It makes it easier. At this point in time, we have x squared plus, this is 3x, and 6x is 9x. Those are gone. Then we got 9. 9 and 1 is 19. Okay, so that would be my expression for f of x plus 3. Right? I'll look at that term so we can see. While I do that, please copy down the homework. Really? How is there no Google response for this? There we go. Braces. Does that sound right? No. For math, it's probably called braces. Let's see. Yeah, that's all it's called. I'll try and find more and see what it is. So again, your homework tonight is at section 3.8. Okay? Your next set is 3 to 42 multiples of 3, 43 and 44. And then only 3 problems in 310. Okay, 3 problems from 310. I'm going to try to grade your test tonight. I don't know if I'm going to be able to get through all of them, but I'll do my best so you can get it back tomorrow. If I don't, I think I'll definitely have to run them.
Yeah.